I want to talk about a fundamental idea in mathematics, particularly analysis. That concept is the nearness of points, what we encapsulate by using in a topological term the word open, because we define an open set to be such that around any of its points there is another open set that's contained in its interior. So in other words, an open set is one in which all the points are tightly meshed together. An open set is dense within itself. So this nearness of points led to all kind of concepts, particularly the limit notion given in arguments in Augustin Louis Cauchy's book that came out in the 19th century, Course Analysis. But the idea, this epsilon delta idea, was first established to talk about the nearness of points, particularly with functions, by Bernard Bolzano. I think it was 1887. And then Carl Weierstrass later on formalized this idea of an epsilon and a delta that you see in calculus. But it always goes back to interval. But interval is a connected set, and most times the interval on the real line is something that is open. In other words, it allows us to establish limits, it allows us to establish convergence, it allows us to establish continuity as well as differentiation. So the nearness of points, namely the open set, is what undergirds analysis. And I try to teach students not only in topology, real verbal analysis, or any other analytic course, that the nearness of points is a fundamental idea where things have to be connected in order for us to have things converge to things, so that we can talk about point-wise the development of the characterization of functions and their properties, even limits that lead us to the definition of continuity, limits that lead us to the definition of derivatives as well as integration. So the nearness of points, or what we encapsulate as an open set, is important. In fact, even continuity, we say what? A function f, say on a space x to y, is continuous if for any open set in the range, let's call it V, the inverse mapping of f on that open set V is an open set in the domain space, about a point. And that's a beautiful thing. So if I take an open set around the image of that point in the domain, well then the inverse mapping maps an open set around that image point to an open set around the point in the domain space. But we're still talking about the nearness of points, openness. So that allows us then to talk about, once again, convergence, which allows us to say arbitrarily we can get near something and we can define something and assure ourselves that it's there. So I don't want to accumulate, so to speak, my philosophical discussion by saying that, analysis is all about open sets. Analysis is all about mappings too, and all kind of configurations. But the key concept, particularly when we're mapping the real line to the real line, is this notion of an interval. I can't say it enough. Without that, I don't think we'll have too much to talk about in analysis. Whether the interval be in one-dimensional space or n-dimensional space, where we have to talk about an open sphere then, perhaps, or just an open set. But the idea of the nearness of point is what undergirds analysis. I can't stress that enough. So the more you master the mathematics of open sets, namely topology, the better you will have strength to understand the marvel and beauty of analysis. I hope that clears things. Again, the most awesome idea in analysis is the nearness of points. Have a most beautiful evening.